About our third gas law. This is called Gay-Lussac's law. And yes, I know, the name sounds funny. He's a French guy, a French scientist who figured out the relationship between temperature and pressure and volume when you look at gases. Now, let's think back to the other two laws that we've had. We did Boyle's law and we did Charles' law. Boyle's law dealt with pressure and volume when temperature was constant. Charles' law dealt with temperature and volume when pressure was constant. So this law is going to deal with temperature and pressure when volume is constant. So again, all three laws, we have the three things that we need to consider: temperature, volume, and pressure. So let's look at Gay-Lussac's law. If the volume is constant, gas in a closed-ridge container, and the temperature is increasing, the pressure will increase. Or if the temperature decreases, the pressure will decrease. So again, we've got all three things. We've got volume, we've got temperature, and we have pressure. Our formula for Gay-Lussac's law is similar to Charles' law, except this time we have pressure, or P1 over T1 equals P2 over T2. And again, where temperature is in Kelvin, remember, Kelvin is equal to our degrees Celsius plus 273. You have to make sure that you turn your temperature into Kelvin. That's the most common mistake that students tend to make. All right, temperature has to be in Kelvin. Let me show you this graphic here. I like this graphic because it gives you a good idea as to what's happening here. So if you look at this container, these arrows represent the particles in the container. They're moving around, they're bouncing around off the sides of the container, and so they're exerting some pressure in this container. But if we add heat to the container, notice the difference in the size of the arrows. The particles are moving around faster, they're bouncing off the walls of the container more, they're bouncing off each other, so they're exerting more pressure. So if we increase our heat, then we're going to increase our pressure. So temperature is increased, that means my pressure is going to be increased as well. Let's look at the relationship. What type of relationship? If temperature increases, then pressure increases. Again, we say that's a directly proportional relationship, just like Charles' law. The relationship between temperature and volume was in Charles' law. Okay, directly proportional. Let's try a problem. If a gas is cooled from 323.0 degrees Kelvin to 273.15 Kelvin, and the volume is kept constant, what final pressure would result if the original pressure was 750.0 millimeters of mercury? All right, so let's set this up just like we did with the Charles law. We're going to identify our temperature, our T1 and P1, and our T2 and P2. So our first temperature, now fortunately we're already in Kelvin, so we don't have to do any converting. So we have 323.0 Kelvin. And I think a minute ago I said degrees Kelvin. Of course that's wrong, right? We just say Kelvin. And our first pressure, here we have our first temperature. Our first pressure is 750.0 millimeters of mercury. And remember, that's one of our units of measurement for pressure. My second temperature is 273.15 Kelvin, and my second pressure is unknown, so that's what we're solving for. So let's look at our formula. T1 over P1 equals T2 over P2. All right, let's make this look nice. That P is ugly there. Let's plug in our numbers into the formula. So we have 323.0, man, I can't get this right today. 323.0 Kelvin over 750.0 millimeters of mercury equal to T2 is 273.15 Kelvin over P2. So that's what we're solving for. We cross multiply, just like we did in Charles' law. So 323.0 Kelvin times P2 is going to equal to 273.15 Kelvin times 715.0 millimeters of mercury. We want to divide this temperature, so 323.0 Kelvin, that'll cancel out, that'll give us P2 on one side. We want to go ahead and divide the same thing on the other side, just like you do in algebra. If you do something on one side of the equation, you have to do the same thing on the other. So 323.0 Kelvin. So when you do the math, my second pressure is going to be 634.2 millimeters of mercury. How do we know it's millimeters of mercury? Well, first of all, my Kelvin unit of measurement cancels out here. There I have millimeters of mercury. Plus we know, since we're solving for pressure, and that's our unit for measurement for pressure, so we know that. All right, let's check two things first. First of all, let's make sure we're at the correct number of significant figures. I have 1, 2, 3, 4 sig figs in my answer. Let's make sure that's right. I have 4 sig figs here, 4 here, I have 5 here. Remember our rule for multiplying sig figs, you go with the smallest number of sig figs in the question. So the question has 4 sig figs. Here we have 4 sig figs, we're good to go. The other thing that we need to check about is make sure that this makes sense. Remember, if temperature goes up, pressure goes up, or if temperature goes down, pressure goes down. Here's my temperature. I went from 323 to just over 273. So my temperature went down. So my temperature went down. That means my pressure has to go down. Let's check that. We went from 750 millimeters of mercury to 634.2 millimeters of mercury. So we're good to go. So it makes sense. It works out correctly. Let's look at our second problem. So our second problem says the temperature of a sample of gas in a steel container at 30.0 kPa is increased from negative 100 degrees Celsius to 1.00 times 10 to the third degrees Celsius. What is the final pressure inside the tank? Okay, first of all, don't be freaked out about this scientific notation. It's not going to be that big of a deal. We'll deal with that here in just a minute. So let's set it up. Identify T1, P1, T2, P2. So here we go. So my first temperature is negative 100 degrees Celsius, negative 100.0 degrees Celsius, let's be precise. My first pressure is 30 kPa, 30.0 kPa. All right, my second temperature is 1.00 times 10 to the third degrees Celsius. And my second pressure is undefined, so we know that's what we are going to solve for. All right, let's change these to Kelvin, add 273 to each one, so that gives me 173 Kelvin here. And if I'm adding 273 here, okay, so if we take 1.00 times 10 to the third, that gives me 1,000, so 1,000 plus 273 equals 1,273 Kelvin. All right, let's plug in our formula. So T1 over P1 equals T2 over P2. So we plug in our numbers. So 173K over 30.0 kPa is equal to 1,273K over P2. So that's what we're solving for. We cross multiply. Right, so we have 173K times P2 equal to 1,273K times 30.0 kPa. All right, I want to get P2 on this side by itself, so I'm going to divide by the 173K. Do that on both sides. 173K Here, when my temperature cancels each other out, so I'm left with my P2 and my Kelvin unit of measurement cancels out, so I'm left with kPa. That's my unit of measurement for pressure. So when I do the math, I end up with 221 kPa. Again, let's check for sig figs. This is a rounded number. When you punch this in the calculator, you actually get 220 points. I don't remember what the number is, but it's a number that would make you round up. So I have 3 sig figs. Let's see. I have 4 sig figs here. I have 3 sig figs here. Remember, with scientific notation, you just look at the number. So I have 3 sig figs here. So that tells me my sig figs is correct. I'm good to go there. Let's check and make sure that the temperature and pressure makes sense. So I go from 173 Kelvin to 1,273 Kelvin. So my temperature definitely went up. That means my pressure has to go up. Let's check and make sure. I went from 30.0 kPas to 221 kPas. It definitely went up, so we're good to go. All right. So there's Gay-Lussac's law. All right, pretty simple, very similar to Charles' law, and we'll see you tomorrow.